at University of Toledo. The main student who did the work is Papubani, master's student, almost finished. The second student who did the finite element simulation is Anish. So we are going to present this together to you. So the topic is evaluation of reserve shear capacity of deep pier caps.
I would like to start an outline. Coming up. We
scheduled this to be a 1-hour presentation.
Start an introduction,
objectives, methodology. I would
about the program that we developed,
which is STM CAP,
followed by verification,
nonlinear finite element modeling,
training session. If you have your
laptops,
follow along. You can watch the video. I think this is recorded. For the training.
Conclusions. So that's the plan. Presentation.
That's
how we divided it up.
Presenting these
parts.
Also would present the more
detailed STM CAP parts, and Anish will present near finite element modeling. So that's the plan for today.
Introduction.
Pier caps. I like these type of structures. You have seen them
around because there are very many of them, and their purpose is to move
girder loads to columns.
Typically set up to be. You don't want deflections.
Girders already deflect, and this supporting structure also deflects. You would end up with excessive deformation. So that's something we don't want. We have plenty of them in Ohio, 28,000 bridges. Nationally, we have about 600,000 bridges.
And if you account for 2 pier caps per bridge, you would end up with 1 or 2 million pier caps easily. And typically in office design practice, we use sectional method.
This sectional method. You have a beam, you draw the shear force diagram, and then you draw the moment diagram, and you determine the critical sections. It might be at the span, or it might be at the midspan, or any other location, and you design the section accordingly. So that's what we do. That's what we teach students to do in their degree studies.
So the issue happens if you use this method to analyze a pier cap. You find them to be overloaded.
So most of them, especially the ones
20 to 30 years ago, you would find them to be overloaded using
the sectional method.
However, if you go on site,
if you inspect these bridges, these pier caps, they seem fine. They don't have any cracking. They don't seem situation.
So the research
is that what is wrong? Why can't we get the right capacity using the sectional method? So that's sort of the problem that we try to tackle. And again, it comes down to the limited budget, limited funding available.
Because if they are finding them loaded, we don't have funding, we don't have budget to retrofit all of them. So we use a methodology
to determine accurate capacity of these type of structure.
So that's the first objective
in our study.
And
it's not enough to determine the methodology, because you need to apply that. We wanted to create a tool so that an ODOT engineer can sit down and use it to benefit from the study that we conducted. Of course, any tool should be verified. We verified it using other procedures to make sure that it runs
successfully, and also we perform considered to be top of the line the most accurate analysis,
as well as we checked it with sectional method just to see what's going to happen if we use sectional method for these thick
structures.
So this is a plot. This is a very interesting plot because it shows a lot. This is done by Professor Kani long time ago at the University of Toronto, Canada. And what he did was to test a number of beams with different depths. And he just plotted the experimental data with those square points. And if you look, the horizontal axis represents shear span to depth ratio. So this is important because that represents how deep the beam is. So if you look, this beam has two shear span to depth ratio. The first one is A1 divided by effective depth. The second one is A2 divided by effective depth. So he just plotted these experimental results. And then he ran hand calculations. He analyzed these beams using traditional sectional method, and that's what he got. And then he used Strut-and-tie method, and he analyzed the same beams using STM. That's what he got. As you can see, there are some regions in which they perform very well. So if you look at the sectional method, this region is perfect. So if you look anything above shear span to depth ratio greater than 2.5, it's perfect prediction. We should use that. We should use sectional method as we do on a daily basis. But less than 2.5, sectional method is going to be super conservative because this is the shear capacity. It's normalized based on concrete strength F prime C. The larger the value, the larger the capacity. So if you take a pier cap in this region, analyze it with sectional method, this is going to be your capacity, right? And if you analyze the same thing using Strut-and-tie, you are going to get 3 times larger capacity. So that experimental plot, although it has been done, it was done a long time ago, it really shows the full story. So this is the region that we want to benefit from the deep beam action by using the Strut-and-tie method. So this is just a summary. If you have a beam, you just check shear span to depth ratio. If it's less than 2, which is usually the case, you would find these type of structures to be deep. We have seen lots of ratios around 0.5, 0.6. So usually less than 0.02, and then you would consider them to be a deep beam. If larger than 2, that is considered to be a slender beam. For deep beams, ODOT gives 2 recommendations. ODOT says you can use Strut-and-tie method, which I will show you. That's what we did. Also, the second option and nonlinear finite element analysis. Also, I would discuss the results with that. If it's slender, there's no issue. We know how to analyze them. We just use sectional method to analyze. This is just a practical methodology to determine the disturbed regions, the deep regions. So you can just draw a square area, which is h by h, right? And you just need to put this on both sides of each point load as well as each support. So you put 1. These are deep regions. See, the entire thing is deep region in this case. You put 1 over there. So you see typically these structures, entire pier cap ends up being deep because the distances are very short in this example. So methodology is to use Strut-and-tie method. This is really a simple method. It is simpler than the sectional method. If you have, I'm sure you have seen lots of historical buildings in Europe, in other parts of the world, and at that time they had no idea what a bending moment is, what a shear force diagram is. The only thing probably they can visualize was tension compression, how the force go from one point to the other point. That's how this method works. Really basic, really simple. So if you have compression applied at this point, you can visualize that it's going to the support using the straight shortest link, shortest path. So I teach this in my classes saying that the stress are sort of lazy. They prefer the shortest, easiest path to go from point A to point T, right? So there's no other path. This would go to this location. This one will spread into 2, so half probably would go here. The other part would go there. So these are the compression forces, how they travel within a beam. And based on this, you see this is a Strut-and-tie model. You put compression elements. And then in between, you need tension, because if you put these compression, this would try to spread up, and then you are going to get tension, and you put your tie. So these are what elements you have to deal with in a Strut-and-tie model. You have to deal with a compression strut, which is the main element. You have to deal with
or size analyze a tension tie, which links it. Otherwise, it would spread open and you would get a big crack at the centroid. And also the nodal zone, because you also need to check the capacity of the nodal zone. So 3 things to check: struts, ties, and nodes. And struts represent compression, ties represent tension, and nodes represent connection. So nodes might have one face might be under compression, other face might be under tension. So nodes are definitely more complicated than struts and ties. So you will spend most time checking the nodes in this. That's just a real Pier cap, and I thought top of that when we were driving today, we might have passed this because these are in Columbus area. We analyzed, I think, more than 10 of them. So this is one of them. You can see, you can determine whether this is deep or not. This is the depth, right? This is H. And just look at this distance, for example. This looks like 1.4, 1.5 H. Yes, that's deep. It's less than 2. So if you look at this distance, it's probably 0.5 H. So shear span to depth ratio in this situation is just 0.5. So this region is super deep because there is really a very steep strut going into the support. So by visually inspecting it, you can understand how deep it is. If there is some distance, you can use a tie. You can send the compression stress at this point, lift it up with a tie, which is going to be tension, that's going to be your stirrup, and then send it again to the support. So that is a stress flow if you have some distance. Still less than 2, the ratio, but if permitted, if you want, this would be an efficient model to do. So you can see these are compression struts. These are tension ties. It can be the main reinforcement, or it can be a stirrup. It is a band. It's not just one stirrup. So you might have a number of 10 stirrup bands, and you just combine them and you represent them with one tie per span. And you have nodes. For example, if you look at this node, this side is under tension. All other 3 sides are under compression. So each node will have a different situation. This is the same thing. This is called compression, tension type of node. The best type of node is everything is compression, so that would give you the best capacity. So this is a nice node, compression. So that's how you deal with it. So STM is complex for daily design. It's a simple procedure, but it's graphical. I think as faculty members, we are partly to blame. We don't teach this in undergraduate education. We don't even mention what Strut-and-tie method is. The reason for this is that deep members are very uncommon. Most buildings, most structures, we always design slender members because they are economical, they are easy to construct. And slender members are analyzed by sectional methods. So pretty much in all universities in the United States, it's typical procedure to teach sectional method for slender members. Don't mention deep members because Strut-and-tie teaching takes a lot of time. You don't want to spend 3 weeks teaching something which doesn't have a big applicability, right? So that's one of the reasons. But 2 types of elements are important because they are deep: pier caps and foundation. So if you end up like you do on a daily basis on a career analyzing these things, the only thing you would need to know is Strut-and-tie method. So there is no check. If you create a wrong model, you cannot really check whether it's right or wrong. So there is a bit of a conceptual model development, which is making it a bit complex. And also, it's an iterative process. You develop a graphical model, you solve it, and it is never a single-step process. At least it takes 2 times refinement or maybe 3 times refinement if you really want to get a very good, efficient model. So these are the complexities. And in this study, we try to explore innovative strategies to automate this, to create a model which is right at all applications, because this is only for one type of structure and we know what model is most efficient, and reduce the complexity to a level which is similar to the sectional method. So as a result, we developed a computational tool which we named it as Strut-and-tie method for pier caps, or STM cap. So Papu spent a lot of time on this. This is the logo that he created for this. It is a code. He wrote about 5,000 lines, 16 modules. It's a computer code. We didn't want to create a new program because you need to learn something new. We incorporated this into Excel, right? So you can just open Excel. Everybody has Excel. Nothing needs to be installed, and you just use it. One thing which is innovative for this code is that it shows you graphically. You input all the dimensions, and you see color-coded graphical structure drawn for you to scale. So you see how the struts forming, how the ties forming, and so on. So that's, I think, the part that we spend lots of time, and you will see input drawing, output drawing, hydros. You can see lots of subroutines just to display the geometry. All right, so at this point, Papa will talk about the overview of the program.
Okay. So as Dr. Gunnar mentioned, we wrote more than 5,000 lines of code to make the input simpler with a fantastic output, following the calculation details. So here we will see a screenshot of the program STM-cap and the engineering design drawing side by side, highlighting the inputs. So let's start. So in the start, we deal with bridge details. Where we can insert general bridge details. These are found in the title block of the engineering drawing. We can find it easily. Then we input the geometry details. These are the number of columns. Based on the number of columns, information drawing is generated with all those variables, C1, W, P1, A1, P2, A2, these variables. And we need to input the parameters of these, the value corresponding to these variables. So in the next, we input the geometrical details of the pier cap. So we input what are those distances. We can compare with the information drawing and the engineering drawing, and we can input those values. Then comes the factor load details. We can insert the load value upon suitable load combinations from ASTO code, and we can again compare the information drawing and our engineering drawing to compare those values and input those values. Then based on these input, like geometrical details and load input, we generate a drawing, which is a dynamic drawing, to confirm the accuracy. If there is any mistake, we can go back and we can like re-input the values and generate again. Then, as mentioned, like Strut-and-tie method, we consider it mostly for deep beams. Therefore, we check like if the pier cap is deep or not. If it is deep, then only we go forward. So we give an instruction like this pier cap is deep, we can go forward. Then going forward, we input the material properties, the properties of rebar, the properties of concrete. All these information are found easily in design drawing. In the tutorial session, we will see like where we can find those things. Then we input the resistance factor, the concrete resistance factor, the rebar resistance factor, and the nodal factors. These are also based on the latest code of ASTO. As the code changes, we can update these factors and we can perform the latest Strut-and-tie analysis. Then we input the reinforcement development, the reinforcement details. In reinforcement details, we input the longitudinal reinforcement details, the stirrup details, and the crack control reinforcement. In longitudinal reinforcement, we input the top area and the centroid from top, bottom area and centroid from the bottom. For stirrups, we count the number of legs and the spacing of the stirrup in any region. In crack control reinforcement, we input how many layers of crack control we have and what are the spacing between the crack control reinforcement. Here we have a sample of longitudinal reinforcement input. We can calculate the total area and the centroid. That's with the input. So after all the inputs are made, what we do is like we internally create a Strut-and-tie model, which is basically a truss model, to perform all the calculation details. So for this pier cap, we develop a truss model inside to perform the calculation details, and we need to find the forces and the capacities for each truss member. So the condition of this truss member is fixed about the condition of the pier cap. As like this truss member might be indeterminate, therefore we use matrix stiffness method to determine the forces of the truss member, and the capacity. And as you see, like the forces are determined. You can see the color change in the pier cap. The reactions are determined. The forces might be in tension or compression. The tension are the ties, and those are represented by these red colors. They're the ties, and the compression are called struts, and those are represented by these blue colors. This is with the force, and the capacity can be determined. These are determined strictly based on ASTO code of section 5.8.2. So, and this is the final and most important output section of our program. So this shows the pier cap boundary shown by the thick line with the girder loads and the support reactions. Inside, we can see a truss model, which is color coded. We can see the ties shown by red color. We can see the struts shown by blue color. We can see the node, which is the intersection of this truss member, which we refer as node, and also the node number. All these are printed automatically by the program. We do not have to do anything. And we can see like those double decimal number corresponding to the truss member. Those are the magical numbers like we are looking for. Those are the utilization ratio. We call it utilization ratio, which is the ratio of force to capacity or load to capacity, or we can call demand to capacity. So if that ratio is less than 1, it means the demand is less than 1. That means we are doing good. So in this case, the utilization ratio is 0.71. It means like it is not fully utilized. It is 71% utilized. We have like 29% more reserve capacity. Therefore, we can increase the load accordingly. We can plan the load. If this ratio is greater than 1, that is sign of overload in that member. And this output drawing is followed by a summary table, which shows in description the information about each member. Like for example, for member AF, we can see what is the load in the member, what is the capacity, and what the utilization ratio. This is like in-depth knowledge about the model. Now we'll watch a video showing the STM cap. Here we have opened STM cap version 14, which is our latest version. It consists of VBA code. This is VBA coded, therefore it works with dynamic graphics. Here we have opened it. With the opening, we see a welcome screen, which shows about where it is developed and the description of the program. Then, starting for a new analysis, we can reset the data. It makes all the input zeros. And then we have like two cell types, input cell and output cell. Input is like orange in color, output contains some formula, and those are like output values. We can insert with the bridge details. You can find the SFN number, PID number, all those in the detailed drawing. You can insert total number of columns corresponding, looking at the design drawing, and you can generate. Based on those, drawing is generated, the informative drawing we talk about. You can also toggle between if that is asymmetric or symmetric. Like for symmetric, we perform the analysis up to center line. For asymmetric, like full analysis is performed. Then we have like all the variables. We can look in the engineering design drawing and find the variables like C1, which is cantilever span, C2, the distance between the second span, the column width, we can find it, and we can select between if it is circular or rectangular, the column. Then it comes to the factor load and their position, where we have to input all this manually based on P1, A1, P2, A2. We can look into engineering drawing and input these values. If the spacing of the girder, which is most of the case, then we can just input these 3 values and we can generate the load table. So it populates the table automatically. After all the inputs are made, then we can generate the drawing. It generates a sketch based on all the inputs we made. So we can see a drawing is generated and it says check for the accuracy. If there is any error, we can again go back and regenerate it again. So if this is okay, let's say the accuracy is right, then we check if the pier cap is deep or not. Therefore, there might be like many reasons. You can see like there are 6 reasons. Some might be deep, some might be slender. But if the majority of reasons are deep, we go forward with the program. So in this case, it shows us instruction if the pier cap is deep or not. If it is deep, we go forward. We make the material input. We input the concrete strength, the rebar strength, the clear cover, stereo bar area, everything from engineering design drawing. There is nothing extra. Then we input the resistance factor, which are based on clause 5.5.4.2 of ASTO code 2017. Again, this can be updated with the new version. Then we input the reinforcement details, which are based on the regions. So if there is like reinforcement change in any region, we need to update it accordingly. So the main concern is like where the reinforcement is changing. So for every region, we can input the longitudinal reinforcement, which is the total area on the top and centroid from the top, the bottom area and centroid from the bottom. Then the other input, the transverse reinforcement. Okay. For the transverse reinforcement, we need to insert how many legs do we have. like in each region. Like in some region we might have like 2 legs, in some region we might have 4 legs. So we need to input the number of legs and the spacing. For the crack control reinforcement, we need to input a drawing is generated inside to show how many legs do you have. You can count the number of legs and the spacing of the crack control reinforcement. And it checks with the minimum crack control reinforcement according to code. If it is greater than the minimum required, then it is good. Otherwise, the reduction in the strength is taken. The next input is bearing plate details. We can input the length of the bearing and width of the bearing. Then we check the reinforcement development. We input the hook length. Based on the hook length, it calculates if it is a straight bar or it is a hook bar. So for those, it calculates the basic development length. And those basic development length goes upon some modification factor to calculate the total development length. We have yes/no option. We can just we can select from drop-down list and we can calculate the reinforcement capacity multiplier. If it is adequately developed, it is 1. Either it is less than 1. Then after all those input, we can generate the output model. Now it will show our Pier cap and the Strut-and-tie model and the utilization ratio corresponding to each member. It is fast. It takes like 5 to 10 seconds at maximum to generate the model. So therefore, we have our Strut-and-tie model and the Pier cap here. Here we have Pier cap, we have the loads, we have the reactions, and then we have all the we have ties indicated by red color, and then we have struts by blue color, and the node which are the intersection of the truss member, and we have the utilization ratios, which is the ratio of demand to capacity, as we talked already. And there is one more thing, like this model can be improved by the use of vertical tie. As we already talked, like there can be many models for the same Pier cap. So therefore we have option for 0, 1, 0, this thing. So 0 is for do not use tie, 1 is for use tie. So you can see we have 4 load path, 1, 2, 3, 4. So here we used 1 vertical tie. So in the second load path we have used vertical tie. For second load path you can see there is 1. So if we do not want to use any vertical tie, we can just select 0 and regenerate again the model. So we can so this works for the optimization. We can select the best model for our Pier cap upon just a couple of iterations. Then we can regenerate again. It in a couple of seconds it gives us new model, new set of utilization ratio, and we can see the utilization ratio and compare with the previous model to find like which one is the perfect model for us, which one is the optimized model for us. So it also checks the top nodal and the bottom nodal capacities. It also checks the top node and the bottom node capacities. So in the top node, we check the concrete on the bearing, on the Pier cap under the bearing. On the bottom, we check the concrete on the Pier cap below the Pier cap, on the column below the Pier cap. So we can see the node A, E, K. These are our top node on the Pier cap, and the others are the bottom node. The calculation details is hidden. If anyone is interested, like where are these data coming from, we can just show and we can click on the button and we can see all the calculation details. So these calculation details are followed from this. We can see how are the nodal compressive strength calculated. It determines the type node types, and corresponding to the node types, we see the compressive strength. We perform the calculation details for the vertical member, also for the top and bottom member. Then we compare it with the node face, and we find the final capacity. We also show the calculation details of the inclined member. Again, we have the inclined member, and we find the width, we find the compressive strength, and the final capacity of the inclined member. We also show the matrix stiffness method. For the Pier cap, we determine the connectivity. We develop a truss model, like we give each node, we give a number, we find the coordinate, point loads, the support condition, and we determine the reaction and the member forces for these Pier caps. So as we talk, like for any Pier cap, there might be any model, right? So this is one model, this might be the other model, this might be the other model, this might be the other one. So which one to select? Like in the first one, we do not have any vertical tie. In the second one, we have vertical tie over the second inclined member. In the third one, we have just one vertical tie over this one. And in the fourth one, we have like 2 vertical ties. So for any model, we need to select that model that gives us maximum capacity or minimum utilization ratio. Like those are inversely proportional. So therefore, like the process of like obtaining the maximum capacity is called optimization, and that model is called like optimized model. So if you compare 1 and 2, we can see like this one has utilization ratio 1.32 in the inclined one. This one has lesser. So of course, like model 2 is better than model 1. But if we compare all the models, then we can see like model 4 is better than like model 1, model 2, model 3, and model 4, because it has minimum utilization ratio in this region also 0.47 as compared to this one, and this has minimum utilization ratio in this case also as compared to 1.32. Therefore, we need to select the optimized model. That would be our best model, and it can be found like in just 1 to 2 iterations. We can just first analyze without using any vertical tie, then using vertical tie, and we can make the decision. In any case, if there is overload, it speaks about what are the overload types and what are the locations of the overload. So, for example, if we have overload in horizontal tie, it denotes it is flexural overload. And if the condition is up to failure, then we can see flexural cracks over the first column. In any case, if there is overload in the inclined member, it shows shear overload. It means shear overload. And if it is failed, then we can see shear cracks over this region on the right of the first column. Similarly, if any horizontal strut is failing, then it denotes a compression overload. And in any case, we can see if it is failing, we can see the compression cracks are over this region. So by seeing this utilization ratio, what we can do is we can plan the load on the bridges. Like if it is failing, we can put a load limit. We can look for the extension, like do we want to like extend it some more lanes, add some more trucks, some more truck load, those things. And also we can facilitate the repair and rehabilitation. Like we can find like this part is overloaded, and we can like take suitable action based on this. Just a summary, like it has very fast analysis and modeling time, as we just see, like it can be done very fast, and we do not need to have any like complicated information about the input and those things. The inputs are simple, and we can follow the step, and it teaches us like how strut-and-tie analysis is performed. And of course, like strut-and-tie analysis gives more accurate results as compared to sectional method for the deep beams. So after our strut-and-tie, after we developed the STM cap, we wanted to check the accuracy, like how accurate is the program working, like if there is any issue or anything. So we checked it with another available software, CAST. It works also on the same principle. It is developed at University of Illinois. So for the verification purposes, what we did is we selected bridge pier caps, and we modeled the bridge pier caps in STM cap, and we found a state of utilization ratio. And what we did is like we modeled the same bridge pier cap in CAST also to find utilization ratio. And in CAST we found pretty much exact, or you can say like almost the same utilization ratio. We did this process for 8 bridge pier caps, and we found very accurate result. In some of the cases there were like slight discrepancy. We verified it using hand calculations, and what we found is like hand calculations showed STM cap results are more better. Then we also checked this with non-linear fine element analysis. My colleague Anish will carry over.
Thank you. So we develop a program that's which depends on strut-and-tie method, but ASTO recommends us to use either strut-and-tie method or non-linear fine element analysis for these type of members. So in this section, we model the same bridge piers cap using non-linear fine element analysis, and we compare. We see how conservative strut-and-tie model is than non-linear fine element method. For this purpose, we choose a software called Vector 2. Vector 2 models two-dimensional. Vector 2 create two-dimensional finite element model, and this program is based on modified compression field theory. ASTO also is based on modified compression field theory. And this program models concrete that is smear rotating crack. And there are many second-order material properties that are considered in Vector 2, like compression, softening, tension, splitting, tension, stiffening. So we can expect a much higher capacity and lower utilization ratio if we perform the study from nonlinear fine element analysis using Vector 2. So we choose a cap beam that was already studied using the software STM cap, and you can see the geometry of the cap beam that we use. These are taken from the engineering drawing, and we create a model in Vector 2. This one is the model that was generated from Vector 2, and you can see the different colors shown here, and this different color shows the different shear reinforcement in different region of the Pier cap. This model was run until the failure, so that we can see what's the stress in the concrete and reinforcement at the failure. So from nonlinear fine element analysis, we generate the stress distribution in the concrete and the reinforcement. We want to see how conservative the results were with the Strut-and-tie. So we convert those stress distribution into a same number called utilization ratio. So here we determine the utilization ratio from the stress distribution that we get from nonlinear fine element analysis. First, we generate the stress distribution at the failure load. You can see that's the stress distribution of the concrete. You can see the red color, which represents the strut action. Then the critical regions were marked in the stress distribution plot. You can see the red circle that shows the critical regions in the concrete, and the same regions that were marked in the failure load were marked in the factor load. These were the zone from where the crack or any failure in the concrete can occur. So we mark this region first, and we mark the same region for the factor load. Then the average stress inside that region was calculated, and which was divided by the capacity of the concrete to get the utilization ratio. So in this way, we find the utilization ratio for the concrete. We follow the similar procedure to find the utilization ratio for the reinforcement also, but unlike concrete, where failure start over a region, in reinforcement, failure start from the single point. So we find that critical single element from our stress distribution of the reinforcement, and follow the similar procedure to get our utilization ratio. So in the figure, you can see that was the top rebar region, and the arrow shows the most critical element in the stress distribution of the reinforcement, and you find the utilization ratio for that point. Next, we compare the utilization ratio that we get from our solution algorithm with the nonlinear fine element analysis, and you can see this is the most critical region, which is the A2 from both the method. The utilization ratio in that region was maximum from both of the method. Black one shows the result from the Strut-and-tie, and the red one shows the result from the nonlinear fine element analysis. The region with the maximum utilization ratio from the Strut-and-tie was same as in the nonlinear fine element analysis, and the region which have very low utilization ratio from the Strut-and-tie have a low utilization ratio from nonlinear fine element analysis. So from here, we found that the behavior that was captured from our program was similar to the one that we get from the nonlinear fine element analysis, and also the governing member was same. And we found that this utilization ratio that we found from the methodology that I described before shows that these utilization ratios were 40% on average of STM of Strut-and-tie, and this was expected since we are considering many second-order material properties from our nonlinear study. So we get more capacity from nonlinear fine element analysis. We performed this test in 5 more bridges with different shear span to depth ratio, and this was the result that we plot between the utilization ratio and the shear span to depth ratio. The green one shows the result from nonlinear fine element analysis, and the capacity calculated were much higher than Strut-and-tie method. And however, the modeling time and the analysis time that was required for the nonlinear fine element analysis was significantly higher. For a single Pier cap, it took like more than 2 days to do this calculation, whereas from STM, you can do that in less than an hour.
All right, thank you very much, Anish. So, sectional method, as I mentioned, it's not appropriate for deep members. It's good for using it in slender members, but just to see the discrepancies in the predictions, we also ran all the database. These are existing bridges located in Columbus area, some of them Dayton area. And we analyzed them using both STM cap Strut-and-tie method as well as the sectional method. So for the sectional method, we determined some critical locations. In this example, this is just I'm showing one of them only, A, B, C, D. And then we created the utilization ratios. The smaller the utilization ratio, the more capacity you have. And if you look at the ratios, in this case, it's 2.5 times larger utilization ratio. So if you analyze section AA using the sectional method, you would find that it fails much earlier than Strut-and-tie method. And I'll show you a global plot in the next slide. So this is my favorite plot because this really pretty much summarizes all the verifications in a very compact manner. If you look at the horizontal axis, this is shear span to depth ratio, right? And I mentioned that if it's less than 2, it's deep. If it's larger than 2, it's slender, right? The vertical axis shows utilization ratio. 1 represents it's at the capacity. So you don't want this to be high because larger than 1, it's overloaded. So let's just compare STM cap with nonlinear. As expected, definitely nonlinear analysis will give you more capacity because there are lots of behaviors considered. There is stress distribution. STM cap will stop analyzing if a rebar yields. But we know that after yielding, a lot of things will take place. Because the yielding is at the very beginning of the response of a rebar. And then it's going to go into strain hardening and it's going to go into rupture phase. So nonlinear finite element considers all of these and it's going to give you the best and most accurate prediction. That's for sure. And it's really consistent around 0.2 utilization ratio for the beams we analyzed. This is not generalized. This is the database that we looked. And on the other hand, if you look at the sectional method, which is the red one, see they are converging at around span to depth ratio 3. So I would assume if larger than 3, sectional method would be very good. But if the beam gets deeper and deeper and deeper, the discrepancy will be bigger and bigger. So in this case, you see you are going to get 3 times more capacity when using the nonlinear method. If you look at the Strut-and-tie STM cap, it is definitely gets closer to the finite element as the beam gets deeper. So as you can see, the accuracy following the blue line, and it converges to the sectional method if span to depth ratio of 3. I would easily say that up to 3, it would be appropriate to use the sectional Strut-and-tie method. Larger than 3, you can use sectional method for this. For our database as it's shown. So at this part, we prepared a modeling exercise. If you have your laptops, if you want to follow along, we can give you the program just to use it for the next 15 minutes. And Papu has intention to, he has the drawings and he just wants to input all the information and then show you how it works, the real program. Just wondering, are there anyone who has the laptop who is willing to do it? If no, no problem. So he can just go very quickly and he can just show how that is used. So maybe Papu, go ahead. And if you want, you can break the screen into 2, right? You can show the drawing in one side and your modeling, you can sit down and you can just work as if you would do. Give us an idea how long it takes and how it works in real life. I'll give you the timing as well for you.
Okay. So the intention of this training program is to see to perform a Strut-and-tie analysis for a Pier cap. We will see how can we get the input, where to find those input, and where to enter those input, and how to interpret the output results. So here I have opened our STM cap version 43, which is our latest version. And I have a layout drawing, a handout drawing of the Pier cap. Here we have shown the plan elevation, the section, material properties, bearing, and the load inputs. I have highlighted those inputs so that we do not have to like look through 6 pages, 10 pages long engineering drawing to deal with. Yeah.
These are just not this SPM model, but just the handout. If you want to, if anybody wants, I can discuss. Right, maybe on the other side, so you can see the input.
It's taking more time to open. I don't know. Maybe maybe the disk is full or something.
I'm suspicious of this, but we need that for the presentation.
Okay.
So leave that open. Let's see what's.
You opened it before, right?
Yeah, it's working.
Yeah, it
I think
popped
maybe
right up.
like the disk is full or something. With the
Here,
RAM and
let's
everything.
just go ahead and try it again. See if it opens. Right click on there. Yeah.
Open an exact, something empty.
Hasn't done this before. This one's my computer. It hasn't done this before.
While you guys are doing that, I guess I'll speak a couple things. Being
Close
involved
this for a second.
in the research project for that side, where
Maybe.
Ashton's always allowed you to do the Strut-and-tie method for DP members, and we traditionally don't because it's more complicated. We like simple analysis. When you get into rehabs that routinely overstresses these elements, and then as an owner, we're left with what do? Do we just direct to look the other way and only analyze the superstructure forces, or do we analyze it, find the number, and do the rehab? We've got the feeling that we're continually doing rehab and replacement on elements that don't need it. We got into here, we wanted to develop a tool that was useful in simplifying that process for us, that are not doing these type of calculations, that don't have PhDs, that just to make it more, to give us a comfort feel with doing something out of the norm.
Excel doesn't.
Yeah.
Maybe
I'll just put it in my web.
I think Philippa's done a great job in
In order to share, you have to draw
providing
the
that with this spreadsheet. It's a very
So
useful
on the meeting
tool.
invite.
I guess I anticipated being used both on the owner side and doing some feasibility work, the scope rehabs, or on the design side for consultants and designers to actually go through, just confirm whether or not these overstresses exist. You can localize it, you can find out where these overstresses are. It has the ability, I mentioned it, where you can change the tie configuration. You can change the truss situation. So where you're not 100% comfortable using the optimized truss, say you do have a couple cracks evident in some parts of the cap, you can tweak it so that it redistributes the forces and models that more accurately without having to go into the effort of the finite element analysis. Again, you could see we were getting 20 to 50% reserve capacity here on this thing, just by looking at it a little bit differently.
Yeah,
and by doing a comparison to finite element, where you have a basis of how much more capacity there is, it gives me a very large comfort zone, comfort feeling with utilizing this, and we have additional capacity left that we're not taking account for. It'll cover some of the constructability and material variability. So I think it's an excellent tool. And I'll throw in the caveat, if I could use this thing, anybody should be able to use this thing. But yeah, I see it. Where I get excited on research is not something that shows that there is something out there that can be done, but that provides something that's useful right now. And I can see this being useful on every rehabilitation project, every deck replacement, every superstructure replacement, widening, that type of thing immediately.
Okay, so now I think we should start. We get it started. So here we have STM cap version 43, which is our latest version. Here we have the drawing. So here we can see the sections, material properties, and the plan and elevation, everything. So with the start, we have Michelle, just 1 second. Yeah, I need to take that off.
Yeah.
Can I?
You can just hold this. Want it like that, huh?
Yeah.
Okay.
Okay. So with the start, we can input the bridge name, and here we have reset all data. Let's first maximize it. Here we have reset all data. So we can click on reset all data. It makes all the input zeros and deletes all the drawings. So we can reset all data. It deletes everything, and it is like a new spreadsheet for us. Then we can start with the bridge details input. We can look at the drawings and we can find this input. So just a matter of to keep it confidential, I'm not inputting those SFN number and PID numbers. Then the first section-wise input is total number of columns. We can look at the our bridge and we can find how many columns do we have. So we can see there are 1, 2, 3, 4 from the plan, and also we can see the same thing from the elevation, 1, 2, 3, 4, right? So we can go there, we can input 4, and here we have option for asymmetric or symmetric. So we can look at the drawing and we can see if it is symmetric or asymmetric. So if we look, we can find it is symmetric from the load, from geometric, from everything. So we can just leave this option as it is. In any case, if it is asymmetric, we can tick this mark and we can generate this. But for this case, it is symmetric, so we are generating as it is. So it says successfully generated, go ahead. So therefore, based on these inputs, we need to input the geometry details and the load details, section 3 and section 4. So for section 3, here we have the description and the variables, like we saw C1, C2, C3, WEST, and also we have the same thing in the informatory drawing. Now we need to find this input based on the drawing. So in the drawing, the first in the STM cap, the first input is C1. So C1 is the distance from, this is the length of cantilever from the start of the pier cap to the center line of the first pier. So here we can find by the red circles, we can see it is 4 feet. Let me just zoom in. So we can input this as 4 feet. The other input is C2, which is the distance between center line of the first column to the second column, which we can see it says 3 column spaces 17 feet. So the distance between these two are 17 feet. We can input 17 feet. Similarly, third one, C3, which shows from center of the second column to the center line. So the total is 17 feet. Up to center line, it will be 8 feet 6 inches. So we can input 8 feet 6 inches. Then the other is column width. We can find this in section drawing. So in the section drawing, we can see the column width is 3 feet and it is circular, right? So we can input as 3 feet, which is 36 inches. And from the drop down, we can select if it is circular or square. So for now, it's circular, let it be. And the depth of the pier cap. So this can be found from the elevation difference. So we can look at the elevation drawing here. From the elevation difference, we can see the top face is 759.54 feet and the bottom one is 755.50. From the red circles, we can divide it. We can find 4.04 feet, which is 48.4 inches. 48.4 inches. Other one is thickness of pier cap. So thickness of pier cap we can found in this one. Sorry. In the section drawing, it says 3 feet, which is 36 inches. We can input 36 inches. All these inputs are like from the engineering drawing. So we make section 3 input. Now section 4 input. If the column spacing, if the girder spacing is same, then we can input just these 3 input and we can generate load table. If the spacing is different, then we need to input manually based on these. What is P1, what is A1, what is P2, and those things. So in our case, we can see the column spacing is same. It says 4 beam spaces at 13 feet 8 inches. So we can proceed with just 3 input. So the first question is like distance of the first load from the edge of the pier cap. So the distance of first girder from the edge is 1 feet 10 holes 3/8. So this is 1 feet. No, sorry. So this is 1 feet and 10.375. Right. Spacing between the girders, we already saw it is like 13 feet 8 inches. We can input 13 feet and 8 inches. And factor load. So this load we input, it should be factored prior to input. So we can select any suitable load combinations. And here upon suitable load combination, we have selected load to be 400 kips. So we can input 400 and we can generate the load table. So it will populate the load table. We can see like the load tables are populated here. In any case, let's say here we have 3 loads up to center line. Here we have 1, 2, 3 load in the center line, and here also we have like 1 load, 2 load, 3 load values, right? Let's say if the middle column, if the middle girder is like 500 kips, we can just manually edit it to 500 kips, right? But for now, like it is 400 kips, like, let's keep it, and we can generate the drawing. So based on the input made, we got a generated drawing. We have the load values. We have all the dimensions showing here. We can compare with these. So it is accurate for now, like we inserted anything. If there is any mistake, we can go back. And as we discussed, there are like many regions. Some may be deep, some may be slender. But as a whole, you've seen this region is deep. Therefore, we can go forward. We can input the material properties. So let's go to the drawing and find the material properties. It can be seen by a light blue color. So the material properties, the concrete strength is 4000 psi. Here we have the option in KSI. So therefore, we can input 4 KSI. Similarly, rebar strength, it is 60,000 PSI, which is 60 KSI. Similarly, for the stirrup, it is 60 KSI. We also input clear cover. In the drawing, like there is no explicit information about the clear cover. So upon experience, like we input this to be 2 inches. And there is like one more information, stirrup bar area. So as seen by the light blue color, we can see it is P501. So that means it is number 5 bar. We have another tab here, like which shows rebar area and centroid. We mostly use this tab for calculating the total area, centroid, and corresponding to the like the bar size. So the stirrup is like number 5. We have area of 0.31. So we can go back and we can input it 0.31. And these are the resistance factor as discussed. These are based on ASTO. And for now, like we do not need to change these, so we are going with the same option. If there is like new version of the code, we can update this and we can go ahead. Then the next input is reinforcement details. These are to be input region wise. Like if there is any rebar changes, that would be like our main attention for this part. So let's see the drawing. So in the drawing, if we see we have number 9. Also in the top one we have the same bar. It is going throughout, like there is no rebar changes, right? We can see the same drawing, same thing in the drawing, in the sectional drawing also. So we have like 2 layers in the top, 2 layers at the bottom. Again, we can go to the rebar area and centroid tab, or we can follow like this hyperlink to go to the tab. So in the first layer, in the top layer, we have number 9 bar, which has an area of 1 inch square. This is going to be 1. We have 6 number of bar. I think it's like already calculated. So we have like 6 number of bar, and the distance from the top, like 2 inch for the clear cover, and 1 inch from the top to the center of the bar can be considered. So that is like going to be 3 inches. Similarly, for the second one, we have number 9 bars, P9. We have 6 bars, 6, and the distance between these 2 layers is 4. So therefore, 3 plus 4 is 7 inches. And as a final, we calculate the total area is 12 inches square, and the centroid from the top is 5. So we can go to tab, and we can input 12 for the area and 5 for the centroid from the top. And in the bottom also we have like same reinforcement, right? So we can input the same value, 12 and 5 from the centroid. Since the rebar is constant, we can just copy. We can copy this value and we can paste to other cells. It's always better to paste by values, right? If there is any rebar changes, we need to re-input those values. Let's say like in 1 and 2 regions we have same rebar, and after that the rebar changes. So for 1 and 2 region it will be same, and for the other regions it will be different, right? And another like this is like stirrup details. We can count the number of legs, how many legs do we have, and what is the spacing. So in the drawing, if you see, we have 1-legged, 2-legged, 3-legged, 4-legged reinforcement, right? And in this, in here we can see like the reinforcement. The stirrup distribution. It says 4P501 9 inches. So it shows only for this region, but we will consider like it to be constant throughout the Pier cap. So it is like number 5 bar, 4-legged number of 5 bar is spaced at 9 inches. So for every region we can select like it is 4-legged and the spacing is 9 inches. Again, we can copy and we can paste by values, right? So that is with the stirrup details. For the crack control details, we need to input like what is the bar area, how many layers do we have, and what is the spacing. So again, we can go back to the drawing, and we can see in the sectional drawing we have crack control reinforcement, which is provided only in 2 layers. Like one layer is this one. You can see like these dots are the crack control reinforcement. This is one layer, this is the other one, and this is number 6 bar. So we have 2 layers. I will input 2 for now. And number 6 bar. So number 6 bar corresponds to 0.44 area. We can go back. We can input 0.44. And for the spacing, we can find the spacing from the sectional drawing. We already like calculated this rebar is like 7 from the top, 7 from the bottom, and the total depth is 48, right? So subtracting 14 from 48, it gives us 34 inches. And we have 3 spacing, like 1 spacing, 2 spacing, 3 spacing. So it gives an average of like 11 inches spacing, right? So here we can see like the crack control provided is 0.22, but the code requires it to be 0.30. So it is not adequately provided. So it will result in reduction in the strength. We will see it. And the next input is base. So the next input is bearing plate details. We need to input length and width, right? So again, we can find this from the drawing. We can see the length is 1 feet 4 inches, which is 16 inches. The width is 1 feet 9 inches, which is 21. So we can input 16 inches for length and 21 inches for width. The next input is reinforcement development. So for this one, what we do is we check the bar if it is adequately developed, if the tension bar are adequately developed or not. If it is not developed, there will be like certain reduction. It will do it automatically. So the first input is diameter of the top longitudinal bar. We found it is number 9 bar, right? We can go to number 9. We can see the diameter is 1.128. We can go back to analysis tab. We can input 1.128. The length of the hook provided, right? So we need to input like how much hook is provided here. So again, we need to go to back to the drawing. We can see for this part, this almost provided. We can consider it up to the clear cover, right? So if we see the gap for this and this, we see it is 3.5 feet, right? So for the top, we can consider it to the centroid of the top bar, which is 5 inches, and from bottom we get at an average of 33 inches. Yep. So input it. We got the basic development length, right, which is 21 inches. And here we have factors like R bar, epoxy coated, and others from ESTO. We can select yes or no depending upon this. So let's consider the bar to be epoxy coated. We selected yes, and this will like calculate the total required development length. So we can see the total required development length is 18 inches, and what we provided is 29 inches. So it is like adequately developed, and the reinforcement capacity multiplier is 1. Like it is adequately developed. There is no reduction in strength. After all the inputs are made, we can generate the output drawing. Here we generate. So it says successfully generated, and scroll down to get calculation details and everything. And it also says like note the STM model can be improved from vertical tie options in section 13, right? So we can improve the model. That means we can optimize the model by using the vertical tie option. Here we see our model, the utilization ratio and everything. So we can note down the utilization ratio. For this one 0.53, for this one 0.72, 0.78, 0.76. If the load is like too near to the support, there is no need to use vertical tie, because in most of the case that would be like ineffective. So we will try using vertical tie for this part, and this part, and see like if using vertical tie is effective or not, right? So let's go to section 13. We'll discuss about this later. And here we have like 1, 2, 3, 4 inclined member. And here we have 1, 2, 3, 4 for the vertical options. So this is like 0 is for do not use tie, 1 is for use a tie. So let's use vertical tie in 2, 3, and 4 region. So we can input 1 to use vertical tie in second one, also 1 for the third one, 1 for the fourth one. It says some changes have been made. Please regenerate the output model. So therefore we can go back. There is option for regenerate output model. We can regenerate it again. It will take a couple of seconds. It will update the utilization ratio, and it will bring another dynamic drawing. So now here we can see new sets of utilization ratio. So for this region, like it was 0.72. For this region, it was 0.78. For this region, it was 0.76, right? So for this region, the utilization ratio is lower than the last time. So this region is like optimized. We can use vertical tie for this region. For this region, we can see like this vertical tie is overloaded. It is 1.99 something. So it is not wise to use vertical tie for this region. So we can select not to use vertical tie for this option. For this option, it was 0.74, and it looks to be optimized. So we can use vertical tie for this option also. So now let's remove vertical tie from this option. So we can go back. We can input 0. We can update the model again, regenerate output model. And it shows like new state of utilization ratio, and this is the the most optimized model for our Pier cap. And it also shows the calculation details, like for member A of what is going on, what is the force, what is the capacity, what is the utilization ratio. So this shows these details for top members. These are all the top members. These are the bottom members. These are the vertical members. These are the inclined member. We also check the bearing areas. Like we check what is the concrete response under this bearing pad at A, E, and K, and what is like the column concrete response under these Pier caps at this portion. So therefore we check it A, E, K, and 2, 6, 8, 12. So here we have like response and utilization ratio for A, E, K, and 2, 6, 8, 12, right? And like this one corresponds to like this one is the top bearing. the concrete, this one, and these two denotes about bearing on the column concrete under pier cap. If interested, we can always show calculation details, and we can go forward. We can follow up on that. That will be, Dr. Gunnar will carry over. Yeah, and yeah, so also in the commentary region, like to follow up, how are the inputs coming and what does it mean? Like, how can we interpret the output? We have the commentary session. It shows like detailed information. What does the reset button says? And it is like provided section wise. So for every section, we can read the commentary and we can see like the instruction, like what does it say? What does it mean? So this will help us with the input and interpreting the output results. And also we have one more tab about that shows description of the program. So that is with.
And in addition to this, we have Opus thesis, which is about 100 pages. What's the total page number?
It's
300.
Yeah, but I mean, total.
So in appendix is the entire printouts of the database. How many bridges you modeled in total?
We modeled 8
So 8, and the initial version for this was for H2 2014. So that's how we developed it initially. So Appendix A will have results for 2014. And then we updated the program using 2017. And we analyzed them again. And Appendix B has information for 2017. So there has been changes. The capacity has changed, the methodology changed a little bit. So we have one little section in ODOT report as well as Papu's thesis discussing it, but it wasn't really our objective to compare two different codes. The end result is based on 2017. In some cases, it's more conservative. In some cases, it's less conservative as compared to 2014. So there's really no clear comparison that I can tell you. So maybe just one thing I need to mention, which wasn't mentioned in the presentation. Strut-and-tie model is very effective. That's for deep members. There is one requirement, which is the rebar development. So, you know, consider a big, thick member, right? Put the load at the midspan, support it from two ends. That member will not bend. The load will go into the supports, and you would need a tie to prevent splitting up. The main thing with the strut-and-tie, or the main thing with the deep members, the tie force is constant. So if it's 100 kips, you have 100 kips from one support to the other support, right? This is different than the sectional method. In the sectional method, you draw the moment diagram, you are going to get the maximum rebar stress at the centroid, and your rebar stress would be 0 at the supports, right? So it is very different. So for the strut-and-tie method to work, for a deep beam action to work, you need rebar to be developed. If the rebar is cut at the node, if you don't have the full capacity developed at this point, because this is compression area, at the edge of the compression, this is transition from compression to tension. If you don't have enough development length, you are not going to develop the deep beam action. It is going to deflect. It's going to be a slender beam. So that's one exception, and the program checks it. You input the hook length, and if you don't have enough development length, it calculates the ratio. If you are 20% less, it reduces the tie capacity 20%, right? So it is based on the code. It's not something we came up with. So the code reduces the capacity, but I think in most cases we looked at 8 at least. I think the database we had 13. We presented 8, but we looked at all 13. Did you see any issues with development in general? So it was good. The issue we saw with the crack control reinforcement. So the crack control reinforcement in older pier caps, it is not adequately provided. Also in this example, so the ratio will change the results. So you are going to get less capacity. If you play with this, so if you are using the software, you can just play with the number and you can see how it changes the results. So if you make this adequate, if you provide more, you will see the capacities will increase with this. So I'll go back to the presentation, and we are pretty much done. I will present the results, and then Mhm. 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 Yeah, so conclusion, just one slide. I think we are done. So, in conclusion, this is STM CAP. It uses Visual Basic, quick and easy optimization. It teaches users. It runs very fast. You can load rate bridges as well as you can do rehabilitation. We validated this using nonlinear finite element as well as other tool. We checked it with sectional method and we saw that up to 3 times more capacity you can get from STM CAP. Accuracy, of course, nonlinear finite element is the most accurate. There is no question about it, but you need to spend 2 days developing a model to get that accuracy, which is doable if you have a complex situation. STM CAP reduces the time to a level which is comparable to the sectional method, but the accuracy is similar to the finite element. So it's not as accurate as finite element, but it's a good spot between the time spent as well as the accuracy you get. So I would like to finish by taking the panel members, Ms. Andrea Parks and Matthew Blight, for their every month meetings, feedback, reading the documents. So it was a lot of work in the past 1.5 years. So thank you very much, as well as Michelle Lucas for organizing all the meetings, putting things together to make this project successful. So at this point, that's the end, and we are ready to take any questions. No, self-weight. So the question is, how do you account for the self-weight of the Pier gap? My answer is it should be into the loading that you provide. So when you are creating the factored loads, you do your combination, which is dead load times a multiplier plus live load times multiplier. So you need to incorporate that into your load calculations in loading input. Another, yes.
Is that the subway of the cap itself, or does your program calculate that? You know what I mean?
No, yeah, exactly. You need to input it. It's not automatically calculated. So the self-weight of the cap, you need to put it separately, divide it between your point loads. Yes, maybe that's a very good point. If we don't have it, we can put it in the commentary section. Maybe we have it already, but we'll take a note about that. That's a good point. So the question, can I get the question one more time? Yeah, so the question is, the supporting columns are made out of concrete for this program. Can I also consider columns made out of other materials, such as steel or other type of materials? The answer is yes, because we are not checking columns. We are not analyzing columns. Columns just provide support. As long as you pick the right area, we have 2 options. It can be a square area or it can be a circular area. So as long as you put the right area, that is it. You can get the reactions and you can check your columns separately based on another approach. You're welcome. Any other questions about the program? Yes.
Now you were mentioning that you use the 2D finite element analysis, not linear finite analysis. Now, if you do 3D, it will give more insight of it. Because I would say, because I have done 3D finite element analysis, we have published papers on, especially I did with my student at Nebraska University. I was a faculty there before coming here. So we did a 3D finite element analysis and 2D finite element analysis, and we put Strut-and-tie model as well as the other model you have done. Now, my question is, when you are load applied on this, you are using bearing pad. So the bearing pad actually is softening the load coming from the bridge deck. Because it is like an isolation pad, but vibration not transferred. So this is a static model, right?
Yes.
So have you done any load analysis for the steel bearing where there is no softening there? And any vibration effect on this?
Okay, that's an excellent question. So let me repeat the question. How do you... They came through clear. Okay, so I'm not repeating it. So the vibration effects should be incorporated into the load. You have impact factor that's built into your formulation, and you need to, I think it's 1.33, it depends on the situation. So you need to increase the load. It's a static model, and you need to put that, and it assumes it's uniformly distributed across the bearing plate. You input the dimension, it's an area force. It's not checking the bearing plate. The bearing plate is not part of the procedure, but it checks the concrete underneath. So if you provide a very small bearing plate, play with the software, put really small dimensions, put the load on it, and it's going to crush the concrete underneath. And you are going to see utilization ratio more than 1. So again, you need to input the right loading. Load analysis is very important. You might have the best STM model in the world, but if your loading is not really right, you need to try multiple loads. Probably it's not just one load case. You need to have like a spreadsheet, load case 1, 2, 3, 4, and then create maybe 5 different tabs, load case 1 STM, load case 2, and then decide which one governs. Any other questions about anything, finite element, Strut-and-tie, or utilization of the software? All right, if that's it, thank you very much for your attention. The documents would be available. We are going to have an ODOT report, which is a short 30-page document, so that's like a summary. Papu's thesis, you can find appropriate sections, so maybe not all of them might be applicable to your situation, but you can look at the table of contents, so that will be available. And STM cap commentary will be the third resource available for this. And also, we shoot a video. So Papu modeled a Pier cap, and that's sort of like a tutorial video, and I think it's about 22 minutes. Yeah. So we are also hoping to make this a part of the documentation so that you can watch it being modeled. Thank you very much.